with, we have an ampersand complex. So I'm Mohammad Samizadeh Nikoo. I work together with Professor Elisa Mathieu at ETFL, and the title of our work is gallium nitride displacement-field nano-switches for Terahertz electronics. So here in this background, we see our experimental setup, and I'm going to discuss about the device that we have right here. So if you take a look at the progress of the communication system over the past decades, we clearly see a considerable increase in the operation frequency of these systems. And this is essential because we need to deal with the massive data exchanges. So we need higher bandwidth, so there is no way other than going to higher frequencies. And currently, 5G operates up to the millimeter waves, and the future 6G communications is supposed to operate at the terahertz band, which can potentially give us a very high bandwidth. And the problem is that right now we don't have high-performance electronics that can have a robust performance at terahertz frequency. So here we have the F-max of the transistor that is provided by foundries, something that we can have in large scales. And we can see that the F-max values can barely reach like below 300 gigahertz or something close to that. And if we focus on gallium nitride transistors that can achieve like higher powers, the FD and F-max are even lower. And because of this limitation, so the alternative is that we can, instead of that, we can use switches like Schottky barrier diodes that as a switch they can provide cutoff frequencies in the terahertz range, and we can do frequency multiplication using these devices, and we can eventually go to the terahertz bands to have the electronics. So here is a very simple schematic of the system that we are talking about. So we have a microwave synthesizer with ordinary electronics, and then we amplify the microwave, and then there is a switch, it's a frequency multiplier that generates the harmonics. Like from 50 gigahertz, we go to the terahertz band by generating this harmonic, and then using a bandpass filter, we select one of these harmonics at the terahertz frequency, and then we have our CW terahertz. And then we need to have a switch to, in fact, perform the modulation that we want and to have the data transmitted in the terahertz frequency. And if you look at this scheme, basically the performance is limited by these two switches. So we have R on in the on state and we have C off in the off state. And the cutoff frequency is defined as 1 over 2 pi R on C off. So this frequency is the frequency at which the on state impedance and the off state impedance are equal. So the switch is not alive anymore. So it's like the final frequency that you can achieve. And in fact, the device works much below that. And this is like a state-of-the-art that we have among conventional switches. And you can see that the cutoff frequencies are in range of terahertz, which means that they can operate much below that. And now we want to see how we can push this limit to higher frequency, 10 terahertz. We want that to be able to have a good, robust electronic cutoff frequencies like 1 terahertz. So the idea here is that, so we have C off and R on plated to improve the speed of merit. And to be honest, for C off, there is a very small amount. At the end, we will be using it. But there is a way to improve the R on of these devices, and to do that, we should see where the limitation goes. So basically, if we take a look at the devices, so we have the channel. On top of the channel, we have contact resistances, which are very important. Professor Gino mentioned earlier in this session how difficult and important it is to have low contact resistances. And if you look at the state-of-the-art of these contact resistances, which limit the conductance of the device, we have numbers that are like larger, considerably larger than 30 ohm micrometer. Normally, a good number is like 100 ohm micrometer, which by itself can dominate the active region of the device. So we have a very good channel, but to access to that channel, we have two contacts or one contact that in fact can dominate the device. And this is like a high performance gallium nitride transistor, one of the base achievements. And you can see that the source and drain resistance is dominating active region. One way to in fact, bypass this limitation from the tunneling junctions, tunneling-based contact resistances, is to use displacement fields to couple the hot metal to the semiconductor underneath. So here we basically have a Schottky barrier, so there is no like connection in terms of tunneling between the metal and the electron. And here we basically have the cross section, and we couple the terminal 1 to the PD electron gas coupler needs through the displacement field that we have in a very thin drawn from the field. And in fact, through this displacement field, the power that we inject to this switch from port 1 here gets coupled to the 2D electron gas and goes to the other side, and again through displacement fields goes to terminal 2. And then we apply a bias to terminal 2, for example, with the P2 today, we eliminate the displacement field coupling in the terminal 2. So we fabricated such devices that are also known in the literature as metal semiconductor contractors. And in fact, here we have the conductance versus the scaling, the widths of the devices. And as we expect, by increasing the width of the device, we have higher conductances, which is linear and it's compensated by the capacitance. And at the end, we have a cutoff frequency about 2 terahertz, which is more or less about good high performance Schottky barrier. Our finding was that if we replace this straight gap between the two terminals by a strike array, a finger structure like this, we can eventually break the trade-off between capacitance, off-state capacitance, and on-state resistance. And as you can see here, by in fact increasing the number of fingers, we can have a super linear increase in the conductance. It's not linear anymore, it's super linear, but the capacitance is linear, and the result is that you obtain much higher cutoff frequencies when you scale the device. And here we see where we are in the C-off R-out plane. And the idea behind this super linear increase is activation of a sub-wavelength mode in the barrier. In this case, you can see that the electric field pattern is totally different from the straight gap, and we present the detailed concept in our upcoming paper. But here I want to focus on the technical aspect of this finding. So we realized scaled down devices. Here we see the device. It's about 100 nanometer size channel, 120 nanometer size channel. We perform measurements up to 1 terahertz. So these are normally very difficult measurements at such high frequencies. And what we see is that up to 1 terahertz, we have a very notable switching, which is already a very good achievement. And the extra cutoff frequency of 18 terahertz for these devices, which is a very high number comparing to state-of-the-art electronics. And as I mentioned, the idea behind this is that the conductance of these devices are very high. So as you can see here in the contact resistance versus total resistance, our devices show a very good performance comparing to state-of-the-art electronics. And this can get more interesting when we take a look at the breakdown of the devices, because this devices doesn't rely on ultra scaling. So we had about 120 nanometer size channel, and we obtained such high breakdown voltage, 30 volts at the cutoff frequency, which is very nice. So if you work with terahertz devices, they normally are extremely sensitive, and even with electrostatic discharge, they just break. But this is a good number for this device. And we realized a 2-terminal modulator using this device technology. So here we have our device, which is integrated with the coupling waveguide. And on one side we inject the data, and the other side we have the CW terahertz wave coming, and the reflection from the device is basically the modulated wave that we have. And we have the waveforms of the modulations at frequencies above 500 gigahertz, which is a good number for future 6G. And you can see that we can have a clean spectrum of the modulated device. So 2-terminal devices are good, but it's very interesting if we can have 2-terminal devices, because then we can realize more advanced circuit topologies. So we realized 3-terminal devices like these, and we have the terahertz in the stripe array structure, and then we have the gate, and then we have the terahertz out, and we have the cross section of the structure here. So this is just a proof of concept that the gate can be much shorter. In this case, it's 200 nanometer. And we see the switching of these devices, which is 14 times at 0.3 terahertz, which is a good number for such high frequencies, this kind of operation. And we realized the 3/4 terahertz modulator using these devices. So we have a frequency up converter that generates a CW terahertz that goes to the device. Then we have the data signal that is being injected by another GSG probe, and we use a high frequency function generator to supply that. And the modulated wave goes to this probe that is analyzed by this block here. We use the commercial VDI mixer to down convert the terahertz wave at intermediate frequencies, and then we measured what we have using a 70 gigahertz oscilloscope. And the results you can see here. So this is the spectrum of the modulated wave at the output, corresponding to data rates from 2 gigabit per second to 15 gigabit per second, and this is totally limited by the data streamer that we have as a function generator. And as you can see, this shoulder represents the data that we have, which is much wider by increasing the data rate. And here we can see how clean the output real-time voltage is, and also the Q and I components of the device of the output in 1 and 0, which shows a good signal to noise ratio. So by this, I conclude the talk. So we propose displacement field switches. In general, these are like similar to metal to the metal varactors or capacitive coupling, but the idea is that by this finger design, we can change the way that these devices behave. And we've got high cutoff frequencies of 18 terahertz, and then we realize 3-terminal devices, which are interesting to realize nice circuit topologies, and then we have a 15 gigabit per second terahertz modulator, and we believe that these devices are capable of realizing advanced modulation such as Q-wave. Thank you very much.